building data.
Okay, let's try blue. Okay, we'll see how many colors I have to get through during the talk. Yeah, exactly. Nope, other order.
So the next talk is by Yuval Wigderson. Will tell us about the approximate structure of triangle free graphs.
Okay, thank you so much. So I'd like to thank the organizers for putting together this great conference, and also to the staff at the Simons Institute. Every time I'm here, I'm amazed by what a good conference they put on. So thanks to them. And thank you all for coming. So I'm going to be speaking about this recent work with Lior Gishboliner and Owen Hurley. So I don't have pictures of them, but you should imagine that you know what they look like. And it's about the approximate structure of triangle-free graphs. And obviously, feel free to interrupt at any time with questions, or if you can't read my handwriting or anything. So a really important question that I care a lot about is if G is a triangle-free graph, why? And I think you all know the answer, because it has no triangles, right? So, OK, that's a good answer. But there's actually sort of a better answer. Well, OK, it can't be better than this. But there's another answer, which is really what I want you to get out of this talk. So answer prime is because it looks like a smaller triangle-free graph. And if you don't remember anything else from this talk, this is what I want you to remember. So this fits, I think, with the theme of this conference. In general, this is a very general thing that occurs a lot. Sometimes you can explain why a graph is triangle-free by saying that somehow its structure is the same as or similar to some much simpler triangle-free graph, so often of constant size. And so, right, somehow, if all you care about is you have some huge graph and you just want to understand why it's triangle-free, it has sort of a constant size explanation. So there's some sort of constant size simplification of it, which explains the triangle freeness. Let me just give you a few examples. The simplest example that I know of this type of result is a very nice theorem of András, Erdős, and Sós. And it says the following. If the minimum degree of G is strictly greater than, that's supposed to be a 5, 2/5 n. So G is a triangle-free graph. It has n vertices. And if its minimum degree is more than 2/5 times n, then actually G is bipartite. OK, so I'll say in a minute why I view this as an instance of this. Oh, thank you. But let me point out, so this 2/5 is tight. So the example showing that it's tight is if your G looks like this. So if your G has this structure where, so this is what is called a blowup of C5. So if G has the structure that its vertex set is partitioned into 5 pieces, each of size n over 5, you have no edges inside, and you have complete bipartite across, then you can easily check that the minimum degree is actually exactly 2/5 times n. It's triangle-free, and it is not bipartite. And just I wanted to write this. Blowup always means this. So whenever I say blowup, I mean you take whatever graph, so in this case C5, you replace every vertex by an independent set, and you replace every edge by a complete bipartite graph, and you don't put anything else. OK, so this is one nice theorem, and as I'm saying here, it's tight. But then there's sort of an extension of it, or a follow-up, which is a theorem of Hegqvist, which says that if the minimum degree of G is greater than 3/8 times n, then G is bipartite, or G is a subgraph of a blowup of C5. So in other words, sort of if your minimum degree is above 2/5 n, then the only structure you could have is bipartite. At 2/5, this new structure appears, but actually that's the only structure for a while until 3/8. At 3/8, another structure appears. So at 3/8, you can be a blowup of, let's see if I can draw this. So you have 8 pieces. So it's going to be another blowup of an 8-vertex graph. So you have sort of a cycle, and then you also have all the long diagonals. So if you get bored during the talk, you can check. So this is triangle free is not hard, and it's not a subgraph of this thing for any larger size. OK, so any questions about any of this? So it's useful to give these things names. And I will change pens again. So this is just a definition. We say that G is homomorphic to gamma if there exists some function from the vertex set of G to the vertex set of gamma, mapping edges to edges. This is the notion of a graph homomorphism. Yes? Yes. So what it says is that, again, if I have a graph which is triangle free and has now minimum degree at least strictly greater than 3/8 n, then I can no longer guarantee that it's bipartite, because this is a counterexample. But I can guarantee that, in fact, this is the only other structure it might be. It's either bipartite or it is a subgraph of such a graph. So in other words, that's the only graph, the only new structure that appears. And the point I was making down here is that actually, again, this theorem is tight, because at exactly 3/8, a new structure appears. So just to get back to what I was saying now, this definition of homomorphism is actually, you can persuade yourself, this is how people usually say it, but this condition is actually just equivalent to, so G is homomorphic to gamma if and only if G is a subgraph of a blowup of gamma. So another way of saying Hegquist's theorem is that if your minimum degree is strictly greater than 3/8 n, then G is homomorphic to either just a single edge or to a pentagon. Right? And the point is that being bipartite is the same as saying that you're a subgraph of a blowup of an edge. It's exactly what a bipartite graph is. Or you're a subgraph of a blowup of C5, meaning you're homomorphic to C5. So I just wanted to, I'll start using the homomorphic terminology. So I just wanted to rephrase this theorem in this language. Everyone happy with this? OK, great. Just to get back to what I was saying back here, right, the important observation is that if G is homomorphic to gamma and gamma is triangle free, that implies that G is triangle free as well. So this is, I think, hopefully not too hard to check. Right? If gamma has no triangles, when I blow it up, I still will not have any triangles. If I pass to a subgraph, I still will not have any triangles. So if G is homomorphic to gamma and gamma is triangle free, then G is as well. And because of this, I view both of these theorems as instances of this, where the reason why these graphs are triangle free is explained by the fact, is explained by these constant size graphs, like an edge or a pentagon, and so on. Everyone OK with this? Yeah.
So what is like an ultimate result here look like? You want to say there's a constantly many things.
Yes. So this is an extremely interesting question. I won't answer it. You can ask me after. But if you want to look it up, the word to look up is homomorphism threshold. There's a lot that's known and actually a lot that is still unknown. But I want to move on to different things. So come ask me after if you're interested. Any other questions? So these results are very, very nice. The problem with them, I think, especially from an applications perspective, is that they're extremely exact. So these results become false if you even allow like a single vertex to have lower degree, for example. And often we're interested in sort of more robust results that are sort of more approximate or analytic. So I want to talk a little bit about that. So actually, before I get back to triangle-free graphs, I want to talk a tiny bit about graphs with few triangles. So there's this amazing result called the triangle removal lemma, which probably many people know. It's due to Ruja and Semerety, whose names we saw a lot yesterday. And it says the following. For every epsilon, there exists a delta such that if G has fewer than delta n cubed triangles, then I can write G as G0 plus maybe plus at most epsilon n squared edges, where G0 is triangle free. So the triangle removal lemma says that if I have a graph with few triangles, in fact, it really is just made up of a graph with no triangles plus a small number of edges. OK, so this is the triangle removal lemma. I suspect that many of you have seen it. There's a lot that we know about it and far more that we don't know about it. So one thing that we don't know about it that's a major open problem is determining this optimal dependence of delta. So we know that this delta, it's easier to say 1 over, it's upper bounded by a tower of 2s, whose height is logarithmic in 1 over epsilon. That's a theorem of Fox. And it's known that this delta, whatever it is not polynomial in epsilon. So it is at least 1 over epsilon to the omega log 1 over epsilon. So just barely super polynomial in epsilon. OK, and you shouldn't worry too much about any of the expressions I actually wrote. The main thing I want to impress you with is that these bounds are very, very far apart. So we would very much like to have a better understanding. And the other thing that's important is that the lower bound is super polynomial. OK, so everyone happy still? So let me switch to red. So far, this looks like nothing like what I did over here. So the thing that I want to now talk about is what is sometimes called the bounded complexity triangle removal lemma. And this, I think, was first observed by Terry Tao, although I think probably a lot of other people sort of noticed it at some times. And it says, for every epsilon, there exists a delta. But there also exists some m of epsilon, which is an integer. And now what you get is that actually this gamma 0, not only is it triangle free, but gamma 0 is homomorphic to some, sorry, G0 is homomorphic to some gamma, where gamma is triangle free, and the size of gamma is at most m of epsilon. So let me unpack what that means. So now I'm saying that my graph, not only is it some triangle-free graph plus a small number of edges, but in fact, that triangle-free graph has bounded complexity, like constant complexity depending on epsilon, meaning that in the same language as before, this G0 is really just itself a subgraph of a blowup of some constant size thing. And in fact, just to clear up all of the parameters and make the board even messier, so I apologize about that. But let me just forget about delta entirely. Let me forget about this assumption and just say if G is triangle free, then, so now this is again a statement just about triangle free graphs. It just follows from the previous statement. If I give you any triangle free graph, you can write it as a sort of bounded complexity triangle free graph plus a small amount of noise. So you can write for any epsilon, you give me a triangle free graph. I can find a constant size thing, gamma, which is triangle free on only m of epsilon vertices. And the graph you gave me is obtained from gamma by blowing it up, maybe passing to a subgraph, and then maybe adding an epsilon amount of noise. So again, this is an instance of this, where any triangle-free graph is up to some small amount of noise, just like a smaller triangle-free graph, which explains the triangle freeness. OK, any questions about this? OK. Everyone happy? Yeah, Clément? Great question. Yes, there are. So this is a theorem of Hoppen, Kohayakawa, Lang, Lefman, and Stagny, and then sort of improved. Well, this is only on one side, and this is on both sides by Fox and Zhao. Basically, so this is theorem in quotation marks, but basically m of epsilon is 2 to the 1 over delta of epsilon. So I won't tell you a precise statement, but this is morally what the statement is. So this m of epsilon, very similarly, our best upper bound is some crazy tower type thing. And yeah, plus 1, but luckily I can absorb that in the big O. And the lower bound now is super exponential. So it's 2 to the 1 over epsilon to the log 1 over epsilon, oops, basically. And again, this quantity is super exponential. So this grows faster than any exponential in a polynomial in 1 over epsilon. Right. So the upshot is that this structural result that I've told you about is very nice. Any triangle-free graph, its structure, its triangle freeness can be explained by a constant size triangle-free graph. Unfortunately, that constant size, first of all, it's at least super exponential, which is kind of a bummer. And second of all, actually, for all we know, it could be way worse, like tower type. OK. So any questions about that?
Sorry, so these bounds on M are for triangle-free or even with the?
Either one, actually. So for triangle-free, yeah. Yeah. Any other questions? So again, the main thing I want you to understand, this is a beautiful, very powerful result. Unfortunately, we don't understand what m of epsilon is. It's at least super exponential. And closing this gap is the same as closing this gap, because this is really inequality. Like there's upper and lower bounds. So this gap is exactly as hard as closing this gap, and that's a major open problem. I wish I could tell you we solved that open problem, but we don't. But instead, I will tell you what we do, which I think is pretty cool. So this is our theorem with Liol and Owen and myself. So let me write the theorem as OK. Yeah. So let me write the theorem as following. If G is triangle-free and CL-free, where some. So now I'm going to assume that my graph is triangle-free, and I'll also assume, additionally, that it also avoids some specific other odd cycle. Then again, then there exists some m of epsilon such that G. So I'm going to. So I don't want to clutter up this board so much, but I'm going to denote this entire thing as this is what's called an epsilon approximate homomorphism. So this just means exactly what's written there, that G sort of has a homomorphism to gamma, except up to throwing away an epsilon fraction of the edges, or epsilon n squared edges. So okay, maybe this whole mess is that G is an epsilon approximate homomorphic to gamma. So, but what's the theorem? So again, if I tell you that the graph is both triangle-free and avoids some odd cycle, then we can say something like this m of epsilon. So this m of epsilon is equal to, OK, if L is equal to 3, then I tell you that it's triangle-free and also triangle-free. So obviously, you don't learn very much. And so we don't know what this m of epsilon is, but it's at least super exponential. And determining what it is a major open problem. However, if we tell you that additionally, if your graph is triangle free and C5 free, then this m of epsilon is actually just exponential in a polynomial in 1 over epsilon. And we have both lower and upper bounds of this quality with different, like the poly is a different exponent, but it's both lower and upper bounds that are exponential in 1 over epsilon, in polynomial in 1 over epsilon. So that's if I tell you that it's C5 free as well as triangle free. If I tell you that it's also, now it's triangle free and C7 free, again, the answer is exponential. But if I tell you that it's triangle free and C9 free, then the answer is polynomial. And that holds for all lengths 9 and above. So I find this kind of amazing because I'm not used to seeing stuff like this. You have a lot of results where like there's some behavior for triangles and some other behavior for all other odd cycles. But I've never seen a result like this where you have like a double phase transition, where you have some behavior for triangles, some other behavior for pentagons and heptagons, and then a completely different behavior for all other lengths. Yeah, come on. Oh. Yeah, so this whole question is trivial for if you exclude even cycles. The reason being that all of this only makes sense for dense graphs. So because my error is epsilon n squared, if my graph has a subquadratic number of edges, like just nothing makes sense. And if I exclude any even cycle, then I have a subquadratic number of edges. So that's why, yeah.
So I'm guessing like the removal lemma implies testing.
Yes.
Does that imply?
Yes. So this does imply testing. I mean, it's kind of a weird testing question because it's like you promise me a graph is like C9 free, and now I have to test whether it's far from triangle free. That I can do with like a polynomial in 1 over epsilon number of queries. Yeah, so that is true, but like it's kind of a weird setting where like you promise me it's C9 free, but then I have to determine whether it's triangle free. But if for some reason that comes up, then this will indeed give a testing result. Yeah.
Yes, sorry.
Yeah.
If I just promise you it's like epsilon close to C5 free.
Yes. So in fact, basically that's fine. So all of these results, they don't really need it to be like to have 0 CLs. Like very few CLs is good enough. So yes, for some not like delta close, where delta is some polynomial in epsilon, that would work. Yeah.
Is triangle special here, but you do see K and CL?
No, so triangles are not really special. So yeah, okay, so this paper hasn't been written yet. And one thing that we want to do before we actually finish writing it is sort of collect the most general version of all of these results. So a huge number of things should work in greater generality. Not literally everything works in all generality. So that's why I'm sticking with triangles, because there I know the complete picture. But very little here is really special about triangles. Yeah. Any other questions? So the one other thing I wanted to say about this theorem is that, so as I mentioned, there's both upper and lower bounds here for both of these results. And just because this is a workshop on computer science, I should just mention that the upper bounds come with efficient algorithms. So the point is that like this actually can be used to actually simplify like a triangle-free graph. So if you give me a graph that is triangle-free and C5-free, I can efficiently construct for you a sort of a graph on this many vertices, which remembers the triangle-free structure of the original graph. And similarly, once you promise me it's C9-free, then I can really do it with polynomial. Okay, so any questions? Yeah.
This whole definition reminds me of like graph limits perspective. So I wonder whether this kind of results, like how we could perceive graphics.
Yes, so everything here can be phrased in terms of graph limits. I mean, yeah, this is saying that it is, you can subtract a graphon of total mass epsilon and get something. Yeah, that is true. I think this is the kind of problem where I don't think the graph limits perspective, I don't find it particularly illuminating, but it certainly all can be phrased in terms of graph limits. Yeah. Any questions?
absurd question, but is there any like super vague intuition as to why, excluding
Yeah.
or any?
Yeah. So that's a great question. So I was wildly overambitious with my planning for this talk, and I wanted to show you basically 3 proof sketches. So the upper and the lower bound here and the upper bound here. And I'm not going to do that, so don't worry. Let me just, at an extremely high level, show you the proof sketch for why excluding C9 is helpful. So I just want to show you basically the upper bound for C9. So, which I hope will also sort of explain what's special about 9. So the basic idea is, I give you a graph which is triangle-free, C9 free. I can assume without loss of generality that the minimum degree is at least epsilon n. The reason being is that I'm always allowed to delete an epsilon fraction of the edges. So if I have a bunch of low degree vertices, I can just delete all those edges and basically not incur any cost. So let's just assume this. Now what I can do is pick v1 up to vm at random, where m is going to be some polynomial in 1 over epsilon. So this is v1, this is v2, this is vm. And what I'm going to do is I'm going to look at the neighborhood of v1. Let's call that s1. I'm going to look at the neighborhood of v2. That's s2, and so on. This is sm. And what you can easily check is because I have some minimum degree, and if I pick some poly 1 over epsilon vertices, these sets will cover almost all of the graph. So if I pick m appropriately, I can ensure that what remains, this is some junk, which is not in this picture. The size of this junk is also at most epsilon n by picking m appropriately. And now I need to construct for you this approximate homomorphism. So I need to give you what the model graph is. The model graph is just going to be, I'll have a vertex down here, u1 up to um. And I'm going to collapse all of these si's into single vertices, little s1 up to little sm. All of the junk I'll condense to a single vertex of junk. And the only thing is I need to tell you how to put edges in. If I have at least one edge between this set and this set, then I will put an edge between s1 and s2 in the model graph downstairs. And otherwise, I won't put any edges. And so obviously, this graph downstairs has only poly 1 over epsilon vertices. The only thing I need to persuade you of is why is the graph downstairs triangle free? And of course, that's where the C9 free assumption is going to come from. And so if I have a triangle downstairs, it has to go between 3 of these s vertices. So I'll have maybe s1, s2, s3. And maybe they're a triangle downstairs. Now remember that these guys have their tails sticking off, u1, u2, u3. So that's downstairs. So in the picture upstairs, obviously I drew these in the wrong order, but in the picture upstairs, what this looks like is I have my sets s1, s2, s3, and I have vertices that are adjacent to all of these things. And because I have edges here, I have at least one edge there, and I have at least one edge there, and I have at least one edge there. Right? Because that's how I defined keeping edges down here. And now you can see, hopefully, that I've just discovered a C9 in the original graph, because I can go 1, 2, 3, 4, 5, 6, 7, 8, 9. And I've closed the C9. So a triangle downstairs, triangle downstairs gives me a C9 upstairs, which is why why the thing downstairs is triangle free. And so really the thing that's special about 9, like what makes this theorem work, is that C9 is the graph I get by starting with a triangle, killing all 3 of these vertices, and replacing them by these little hops. So that's like why C9 is special. And similarly, like the lower bound that works for 5 and 7, somehow the reason it works for 5 and 7 and fails for larger lengths is sort of, again, because of the same picture. But I won't get into that, and I'll stop and take any questions. Yeah.
So in the theorem, you skip triangle free.
Mm-hmm.
So I don't want to have C9.
Yeah.
What type of bound?
So are you still hoping that the downstairs thing is triangle free or C9 free now?
C now C5.
Yeah. So the generalization of this is it's always super exponential going to be. So if I tell you that a graph is H-free and I want you to model it as an H-free thing, I will always require super exponential. Sorry? Upper bound will again be a tower of logarithmic height. It's going to be exactly the same for any non-bipartite graph. The power here is like there's some asymmetry where I give you more assumptions than I want in the conclusion, and that's really necessary because otherwise super exponential is really the truth.
The M of epsilon just comes from this counting that you need to do here.
I mean, yeah, literally, like the number of vertices is m downstairs, m upstairs plus 1. So, and then just to make this work, you only need m to be some polynomial. Yeah, exactly.
So why does it have to be necessarily a C9? What if it's like those two in the thing?
Yeah, OK. So I cheated a tiny bit. So really, what you would do is you would not keep an edge if there's only one edge between, but if there's some reasonable fraction of edges, that's OK, because you're always allowed to throw away some small fraction of edges. And by doing that, you can ensure that really these things are matching. Yeah. Okay, good catch.
So
Yeah.
that's the only reason why you have to do the full subdivision as opposed to like 5 or 7.
No, I mean, like you can't build a C5 like this, like because you really, right? You really need to hop at least once outside, because if you give me just a completely unstructured thing here, I still might not be able to sort of glue it into a C5. Yeah. So somehow, if this structure looked like I had 3 sets, and each of them were cut in half, and like this left-hand side was adjacent to that, and like this right-hand side was adjacent to that, so I have a ton of edges, but I can't close any cycle without sort of doing hops outside. So that's why I need the full 9 lengths. Yeah.
Is it obvious that the SIs are disjoint? Or does that matter?
So I mean, in a real proof, you have to make this work. But yeah, this is the right idea. Like it's a tiny bit more work to make it like real. Yeah. Yeah.
If you allow epsilon to depend on n a little bit, can you get like a more general statements? So if I allow like I don't know some small difference on.
Yeah. So I think actually like this theorem statement does not require epsilon fixed and n large. So I mean, you get some like from this proof, you get some actual literal constant power of epsilon here, and the theorem is true for any range of parameters. So if you make epsilon some very small negative power of n, then this is like a sensible statement also in that regime. Yeah. I don't know of any particularly nice applications, but it is a correct statement that should work also in that regime.
And do you get also, so if you want to remove the epsilon, that's exactly triangle free, but like the same like as at most delta n cubed, can you?
Yes, I think all of this should work the same if you allow me to assume it has very few triangles. Yeah.
So you said that the way to interpret this as a property testing result is to assume that the graph is CL-free and you will find it in it.
Yeah.
But why not just say I'll take any graph and I'll find either a CL or a delta in it?
Because of the question Artur asked earlier, when I'm trying to test, like testing CL freeness for any L is at least super polynomial for the same reason. So like if you just give me a graph and you first want me to check, like I need to have some guarantee for this to work. Yeah. Somehow it's the asymmetry is crucial. And if you don't allow me asymmetric assumptions and conclusions, like you need at least super polynomial for these property testing things.
Questions?